Uh, Good evening or good afternoon in Germany or wherever you are. Um, I'm going to speak today about multifunctional cement-based materials with a focus on carbon cement supercapacitors. I assume that uh, you don't know anything of supercapacitors, as I didn't know anything about supercapacitors maybe 5 years ago. Um, this work has been done together with my colleague Admir Magic at MIT, collaborators Nicolas Chanou, Damien Stefaniuk, James Weaver, Yang-Xiao Horn here at MIT. Well, I also want to dedicate this talk to a young engineer colleague, Majid Masharawi from Gaza and Palestine, who has inspired much of this work. I'll come back to this later on. So, what are we talking about when it comes to energy storage challenge? I think this is nothing new for you. The problem of the energy transition is that this energy transition from fossil fuel to renewable energy sources, to electron-based energy sources, requires a storage solution for the simple reason that fossil fuel classically combine the storage and the energy carrier in the same place. So when you take 1 liter of fuel, bring it from one place to the other, you carry with it the energy in it, and you have it the source available. This is different when it comes to renewable energies, where the energy carrier and energy source actually are separated. The energy source, for instance, solar, creating electrical energy, need to be stored intermittently, at least for many applications. And we know this immediately from the imbalance between the supply and the demand side in the renewable energy sector. They involve different timescales, whether it is wind or whether it's tidal waves or whether they are or solar. And for that reason, energy storage is a key factor in order to achieve the energy transition. The problem right now is that the energy storage solution that exists, basically based on battery technology, and I'm going to come back to that here, that most of the precursors used for batteries like lithium are available only in very particular parts. In addition, the processing of them are dominantly done in China. So even if you have a lithium source, you still have to transport this, which makes this technology, this battery technology at its current state, very difficult to scale to the level where we need it in order to make energy storage solutions available for everyone and everywhere. And it is here where we come into the play. And I will talk about concrete. Now, concrete, you may be aware of it, is the material most consumed on planet Earth after water. In fact, it is the backbone material of our infrastructure needs, our societal needs for shelter, hospitals, kindergarten, you name it. But at the same time, this omnipresence of cement, which is the precursor for making concrete, this gray powder, this omnipresence of cement and concrete entails a huge environmental impact. Roughly 10% of the worldwide CO2 emissions actually relate to the production of cement. So if a carbon tax, for instance, would be imposed on the production of cement, so on the order of $150 and $200, there would be no concrete future unless there's something done. Well, in the industry right now, the cement industry committed to reaching carbon neutrality by 2050. But like many industrial sectors, has no idea how to achieve that goal. Right now, the solutions that exist are, well, let's replace cement by some other materials. fuel substitution. So instead of heating with some fossil fuel, let's substitute this with other fuels. The point about increased thermal efficiency, I think, is something which you know very well in Europe, as this is a matter of even politicians discuss that matter. Then there are approaches which are based on less is more by design, and then of course the improved longevity of infrastructure, so that one does more in time with the material than before. There are some carbon capture and storage solutions, but that's not what I'm going to talk today about. Today I speak about electrical conductivity, adding a new function to concrete, to this backbone material of and its strength in our infrastructure or in our buildings, adding this new function of electrical conductivity for energy storage, which would help to reduce in the overall life cycle analysis of concrete its environmental footprint. But let's get real here. Concrete is strong, everybody can make it, and we know that. And it has its huge environmental footprint, but it is an insulator, like most oxides. It's an insulator, so it cannot conduct electrons. So how do we add this functionality to concrete? Well, the idea actually here is we need to add another component to it. And what we do is we add the best electron conductive material to it, which is carbon. Actually, carbon black powder, nanocarbon black powder. Carbon black, as you know, is used in many industrial applications. Just think about your tires of your cars. So we add nanocarbon particles in a relatively small concentration. So we add roughly 10% by volume of nanocarbon black to classical Portland cement. We add a little bit of super plasticizer in order to master the rheology of the material, and then water. And then the magic of chemistry takes place, and we achieve an electron conductive carbon cement composite, as you see here. The small amount of carbon black makes the material black, not gray as classical cement, but it is electron conductive. But what happens there actually? This magic of chemistry. What happens is the following. We are dealing here with two different materials, a hydrophobic carbon black, which when you add water to it, clumps. A little bit the same thing what happens when you add water to flour in your kitchen, so it clumps. But if the same water is consumed by the hydration reaction of hydrophilic cement, these clumping forces, van der Waals forces, in the alkaline environment of the cement hydration are released in order to generate actually a volumetric wire. So a percolated system of nanocarbon black particles permeating a strength-bearing matrix. And why is it important to know about this chemical process, that this is a chemical-driven process of a hydrophobic and a hydrophilic phase here, is because it is chemically driven, it is highly repetitive. It does not require an operator in order to do it. And that makes this solution, at least from an electron conductivity point of view, a scalable solution. Well, we can look closer at this material in order to visualize these carbon black permeating this strength-bearing cement-based matrix by means of Raman spectroscopy. As you may know, Raman spectroscopy is a technique which activates by light vibrations at very small scale, and is an ideal tool in order to separate what is the oxide part of it and what is the carbon part of it. It also allows us to distinguish other carbon sources like natural carbonation from CO2 of the material through this technique. And if we do this, actually, what we realize is that this carbon black, this volumetric wire actually permeates at all different scales the system. It's as you see in these lower three pictures here, from SEM, EDS observations, we create a space-filling material which almost has a fractal type geometric texture. The interesting thing about this is that this space-filling volumetric wire is everywhere throughout the material, while allowing at the same time the permeation of or the existence of cement-based strength-carrying skeleton, which can carry loads. So, and what is happening then? Here's a typical graph. What happens here on the y-axis in a logarithmic scale, you see the resistivity, which is 1 over the electron conductivity. And on the x-axis, the carbon black particles in percent of weight of cement. What you see here is classically you have a relatively high resistivity until a percentage of roughly 2.5%. And then you see this drop by 7 orders of magnitude of this resistivity, the inverse being the electron conductivity, which is the indication that at that point, this combination of a hydrophilic and a hydrophobic phase has led to a percolated electron conductive material. So where does that material place? So use here this Ashby plot, which plots resistivity versus cost here in pounds sterling. Excuse this non-European currency. And as you see here, this resistivity, these orders of magnitude of resistivity plays in a relatively cheap cost realm. The cost of cement is roughly $100 per ton of cement produced. We add to it carbon black, which is equally cheap by production. And there are very interesting new ways of getting carbon black, for instance, by the separation of methane into hydrogen and carbon black. So what is interesting here is that this material, this carbon cement composite material, plays in a price range of the commodity market, which makes it available for everyone. So what types of applications you can think about? Well, first one is, if you remind yourself that the material, even at this small percentage, has hydrophobic surfaces, well, one can imagine to simply put them for freeze-thaw resistance on pavements. A second one is self-heating, so-called Joule effect. For instance, for de-icing bridges, sidewalks, airport runways, etc., or radiant floor heating. Instead of having a wire, you just have made material for this purpose. A third one, which I will concentrate today on, is the energy storage, and I will come to the structural supercapacitors. And if you're in the military field, there can, of course, be the use of the Faraday cage effect could be used. But let me focus just here on the civil applications, self-heating and energy storage. So talking about self-heating, so what is this? How does this self-heating goes? Well, the interesting thing about this is that in the moment, if you have an electron conductive material, you can redo with this material your everyday experience of an electric stove. Meaning, if you apply a voltage to the system, you generate heat throughout the sample, and the temperature rises. There's a distinct time scale to this rise, which relates to the boundary conditions, to the thermal boundary conditions of the system. But intrinsic to the process is the observation that the temperature increase scales with the square of the voltage, meaning if you go from 1 volt to 2 volts, you get 4 times higher heat generation and thus higher temperature. So that is, you can do this with a very simple experiment, putting a sample, as I show here on the left side, between 2 conductive papers, and you measure the temperature inside here. But this becomes also scalable to, well, to a pavement structure. We're talking here about length scales, which is like a sidewalk, typical sidewalk, which we try to mimic in our lab. So what I show you here are how many? 6 panels. Imagine them like tiles. And these tiles are connected here to a voltage, and we apply different voltages here in order to show how the temperature rises. So that's in our labs. Then we apply the thermal camera, and what you see here, if I remind you that this was 0, 12, 24, how homogeneous this heat actually is generated within the material. So that is an application which is already ready to go, simply by making use of the so-called Joule effect in order to use this for outside heating. I think it's we don't need salt on our pavements anymore if we were to use this material. Or think about it, if COVID or another pandemic would hit us, we could go into a restaurant and sit outside, having the heating coming from below with a very efficient heating source. If in addition this heating source is provided from a renewable source, well, then this becomes a highly sustainable heating system. There are many other applications which one can imagine with these type of systems in insulation system for buildings, by breaking the difference of the temperature between inside and outside by means of such a thermal layer. This is not new applications. Actually, there have been other people who have tried this before with steel fibers, steel shavings, etc. The advantage of this particular technology of using cement and carbon black, nanocarbon black, is that the percolation threshold is much, much lower. If you take steel shavings, for instance, you need at least 20% of steel shavings per volume in order to get a percolated electron conductive network. The same would be if you use higher quality carbons, for instance, sheet-type carbons, the percolation threshold would be much higher. As a consequence, this system, as we have it here, is highly efficient and would be cost-wise quite interesting. As I said, just for those who are more interested on the engineering side of it, the overall design of such a system would have 3 components. There is some structural parameters like thickness, length of a slab. Then there's a control parameter which is highly accurate, which is the voltage to the power 2. And finally, the material capacity, the mixed design here, which enters the picture. So here, an example how multifunctionality of a commodity material can help us to make the energy transition, for instance, for heating systems. But let me come to the main part of my talk, which deals with energy storage. Already evoked this need to shift to green energy, that this shift requires these massive storage solutions and structures for everyone and everywhere. But is there a future with concrete batteries? And even though I put the word battery here, I want to make clear this is not a battery, and I will explain why. Well, can you imagine that we have these type of highly engineered system in this gray blocks? Well, how does this actually work? So let me make clear how does a battery works versus a supercapacitor. A battery transforms electrical energy into chemical energy. So when you charge it, electrical energy comes in, it is changed into chemical energy. And then when you discharge it, the inverse process takes place, which is why you get a couple of hundred, maybe 1,000 cycles out of it. And the decline of batteries is a major issue for longevity of batteries. And in many applications, we do not know actually what to do with the remnants of these batteries after they are depleted. Supercapacitor work quite different. While we have two electrodes, so two sides of the material, one charged positive, the other one negative, and in between a separator, which allows ions to pass through, but no charge. When you polarize these electrodes, ions from the pore solution or from the solution in between the electrons are absorbed onto these electrodes. So actually counter ions, meaning if you charge an electrode positively, you get the negative ions of the electrolytes or salt solution. You get the negative ions onto the surface. And on the other side, it happens the opposite. So if you charge the electrode negatively, you will get the positive ions of the electrolyte getting onto the surface. If you discharge it, they return into that space. And so you have almost unlimited numbers of charge discharge in contrast to batteries. So there's no chemical reaction taking place. It's a pure electrochemical absorption process. So, but let me be clear about it. We don't have plates like this here made out of concrete. What we actually have is we have a space, the pore space of concrete or of the cement paste to host the electrolyte. This is the natural porosity which is left inside the material at the end of the hydration reaction, the hardening process of cement. So the electrolyte is inside the material. At the same time, we have this percolated carbon network, which is for us the electrode or the conductive part to charge the electrolyte, to polarize it. So when we put on our material a positive charge, then this volumetric wire permeating the material is immediately charged, and it pulls then the opposite charge of ions out of the pore solution of the material. Both this network of carbon black particles and the porosity are a simple result of chemical reactions. And here's a typical example. So as you see here, you see such a prototype of some thin electrodes, which we test in the lab. You see two electrodes in between a separator, which, as I said, allows ions to go through, but no electrons. It is charged from the top with a positive charge, from the bottom with a negative charge. And so here's again just a design. On the top. You have some conductive paper in order to make sure that the entire surface is equally charged with either positive or negative electrical charge. And this is the type of load or result which you obtain then, what you can measure in the lab here. If you go from a 0 voltage for 1 voltage, 1 volt, we never go above 1 volt because the electrolyte is water-based. And if we use a water-based electrolyte, you don't want to go above the theoretical value of 1.23 volts, because then the water would split into hydrogen and oxygen. So we always limit it to 1 volt here. But if you then run the cyclic test where you go from 0 to 1 and back, you see this hysteresis loop in this current voltage plot. Well, the area here in between, without going into too much details, is actually a measurement of the energy storage capacity of the material. And to give you an idea, the order of magnitude here is 1 kilojoule per kilogram of this material, which is 0.28 watt-hours per kilogram, which, if you take the daily residential energy consumption of a typical residential dwelling in Germany or in Europe is on the order of 40 cubic meter of this material. So this is what you would see now. This is a very small prototype system, just charged to 1 volt. But again, how does the system work? You see here this 3D pore network, connected pores in the cement paste, so which hosts the electrolyte. We call it the transport porosity, which is the result of the hydration of the material. And then we store the energy along this volumetric wire. And there the key quantity, which is of importance, is the specific surface, the in meter square per gram of carbon black here. And as you see, let's say for all these different electrodes which we produced, you see this linear scaling, which only depends on the specific surface. So the higher the specific surface of the carbon black which you employ, the more energy you can store along the volumetric wire. After we found this, it was pretty evident that this would be the case. But I started out with talking about multifunctionality. We should also be cognizant of the fact that when you add a hydrophobic material into a material which is hydrophilic, but also cohesive based, meaning creating between the cement, hydrated cement particles, cohesive forces, that when you add this hydrophobicity in it, the strength goes down. The strength of the material, which comes from the cohesion of the material. Which means that on the one side, we need materials which have a very high porosity, as high as possible, in order to get as much electrolyte inside the material for the storage onto the carbon black. But at the same time, we know that the same porosity leads to a strength reduction of the material, which means there exists for each application a sweet spot between the energy storage capacity on the one side and the strength capacity on the other. Now, once you have one element, of course, you can build systems of the supercapacitor. You're not limited here to 1 volt. But what you can do here, as you see in this example, you take 3 of these supercapacitors and put them in series. So these were our first attempts of doing that here. Just put them in series here, and then charge it with the photovoltaic cells in the lab for proof of concept. And of course, when you discharge it, so when you disconnect after some charging the system, you get an LED light working. The reason why we took 3 volt is because, you can make a nice yellow lamp on. You need a little bit more than 1 volt in order to get a red light on. So that's actually a highly repeatable system. But how do we scale this actually to the next level? So our next target then was a 12 volt equivalent battery, if you want. And you see here, these are not Oreos sweets, but these are, each one is sort of this double layered electrodes. So 2 electrodes here with a separator, and then a conductive current collector in between, and you build them up just here upward. So the prototype idea here behind is, in essence, if you think about a column, which are everywhere omnipresent in our buildings, well, you just fill them up with these supercapacitors and connect them on the top to a positive charge, on the bottom to a negative charge, or vice versa, and you can scale it up to whatever voltage you are dealing with. So of course, here you see this end design, you just want to hold them in place. And you insulate the outside in order to avoid that the electrolyte runs out, because we need the electrolyte for the ions to absorb onto this carbon black network. So here, sort of the first prototype developments of this 12 volt, battery, 12 volt supercapacitor, carbon cement supercapacitor. And then, of course, you repeat those tests as we have done before. You charge them now not to 1 volt, but to 12 volt. And because of the series arrangement, each one of these 2 electrodes, of these sort of separator, has only 1 volt in there. But all over, of course, you get now a much higher energy storage into the system. For instance, with that type of system, you can charge an iPhone. The interesting thing about this is that the energy here, which is stored, simply scales in the series arrangement with the numbers of these supercapacitor element. Let me also say that the rate of charging is scaled by the thickness of the electrodes. So here in a lab, we have a couple of millimeter, went up to a centimeter, but in applications, you would want to go to other ones, to other thickness, depending on whether you want to store over a day or whether you want to store in a couple of minutes or seconds. So if you have a column design, for instance, for 240 volts in a building with typical height of 3.60 meters, you would need sort of a column height with electrodes which are 1.5 centimeter thickness, which you fill up the column. I've mostly spoken about cement paste, mixing cement with water and carbon black, but the same thing works, of course, with mortar. Mortar is when you add sand to it, which increases the strength by some frictional behavior. The only thing is you dilute a little bit the energy storage capacity of the system, but this is no problem to design this accordingly. So the same fast energy storage becomes possible with a mortar system, and for thick elements and long storage, we can think about bringing this all the way to concrete. Let me finish around this here by saying that all what I showed you right now is happening well in the lab. And of course, now is the question, how will the future of this technology look like? How will we produce them? Well, you know, you have heard about additive manufacturing like 3D printing. Well, that could be a great technology in order to print those electrodes at a scale of buildings. But it could also be the elementary brick, where each elementary brick has sort of is the equivalent of a 12-volt supercapacitor designed with a certain thickness, each electrode, to reach certain rate demands of the application. The high-end application of obviously we are looking at is the self-charging roads. And it's a phenomenon which you know well when you charge wirelessly your phone. I heard that these are one of the most sought after Christmas presents these days, which come now in a large variety of systems. But how does this technology work? It is what you need in order to charge wirelessly a phone or a car is that you need two electric fields, one for our application in the pavement, the other one in the electrical car. Well, the one in the car already exists. What you then need is, if you have those two electric fields, then by electromagnetic induction, energy is transferred from one system to the other one. That is feasible. It's actually a technology which is already in development, but not with our materials, actually with coils which are embedded inside the pavement. But imagine that you could use the same material with which you built your pavements, you could use as a means to create this electric field at high frequency. It's a high frequency application. And charge a car automatically, meaning when you drive to your shopping center where you do your shopping, while you park there, your car is charged. Or when you drive in your driveway or in your garage, the car will be charged without plugging in the car into an electric charger. Ultimately, ideally, we would like to drive on pavements which charge the cars while driving, which would take away this permanent fear of all EV drivers in M1. Will I run out of juice to reach my place? Another application is windmills for intermittent storage. As you know, the windmills operate right now at a relatively low efficiency. And this low efficiency is not due to the technology, it is due to the fact that wind actually is highly stochastic process. And so we cannot get all the wind spikes transferred into energy because batteries are charging too slow. Well, here's a technology which can do this. So imagine that we could store this energy which is created by wind intermittently into either the foundation, well, imagine column type foundations, we call them pile foundations, or even into the superstructure. Of course, for this type of application, we would need high strength applications for the column, as well as the filling inside here with our carbon cement supercapacitor. And then imagine what type of structures we are looking for. We need structures which have a relatively large surface in order to obtain high power application, to reach high power applications. Think about vascular networks as they exist in our bodies. What type of architecture will we see? So you see, this is a very exciting time to move into this sphere, into this multifunctional design space for homes, for walls, for pavements, how they will look like. I started out by dedicating this talk to my young colleague, Majid Masharawi. She is an engineer and CEO from Gaza City. Actually, she, in 2015, was one of the first who has sort of tried to use, in lightweight concrete bricks, carbon. This was after the 2014 war in Gaza. In 2019, she started actually Sunbox, a company in Gaza with photovoltaic cells, and built batteries together. And when I met her and talked to her about it, she was very enthusiastic about implementing also this technology in Gaza. I haven't heard from her since October 7, so I want to dedicate this talk to her. Thank you very much.
Thank you, Professor Ulm, very much. First of all, thanks also for the dedication. That's very thoughtful, I think, and I'm very mind blown by the technology, and in my mind was ideas where this could be where everywhere to use it, and I think it's very it can lead to very creative, innovative solutions. I would have a lot of questions, but of course the audience shall be first. So if there is somebody with a question, please just raise the digital hand or write into the chat. Okay, so I will start and maybe then someone will move forward. I was wondering, just a very technical question. As the material, of course, has a specific amount of water inside, how does it behave with aging? Because I can imagine water with all its phase changes is a little bit sneaky sometimes. If you talked about the columns, if you imagine you would have it outside, if there are temperature changes, you will have, I'm not sure if the water will have a phase change, if it's inside or if it's chemically bounded or you have supercooling, I don't know, but do you have any experience already how it will behave?
Okay, it's an excellent question. So I don't have the answers yet because we haven't done actually the whole cycles, but so there is a question of freeze-thaw cycles, right? So the idea actually that a phase change would crack concrete. Now, there is this wrong perception actually that this increase of volume from liquid water to solid ice, that this increase of volume actually exerts this pressure. However, as I showed you before, the pore space in concrete is completely connected, which means actually that you don't have this pressure exerting. The reason why concrete breaks under freeze-thaw cycles are so-called forces which relate to the charge, which is the fact that ice is almost charge neutral, whereas the surface of the cement paste of the reaction product is charged. As a consequence, you get a gradient here, which increases the pressure. But now, if I add carbon black into it, I basically neutralize this difference and actually will have a positive effect on these freeze-thaw cycles. Now, this is at least that was actually one of the first applications which we looked with these materials in order to improve the freeze-thaw cycles of concrete materials without thinking about anything about electron conductivity. Now, this is only one aspect. Now comes the electrolyte. It's a little bit more difficult thing. The most important thing is to keep the electrolyte inside the material over the entire lifespan. And we're talking about a lifespan of a structure maybe of 30, 50, 70 years. How do you keep this inside the material? Or to have some adaptive structures where you can change them. So, change an electrolyte inside change an electrode inside the system. So these are questions which are design question, operation questions, which we need to address for each application. But it will be different if for each application, whether you operate in the wind energy or whether you operate in a foundation of a building, which you can never change, right? Or rarely change, right? Or whether you operate in a column which is accessible from the top in order to change an electrode inside the system. So these are all questions which needs to be now developed, which is why I'm saying the engineering starts now of these solutions in order to develop for any specific applications, all the requirements and feasibility here for each specific application. There is not one only measure.
Yes, I see. It's a good thing and a bad thing at the same side. Like there's a lot of applications, but also a lot of knowledge which has to be demonstrated how it's working and what's the optimization.
But think about this. Think a little bit larger, right? The energy transition is a decision by a society to ensure its future, which means everybody should be involved. And here you have a material everyone can produce. It's not just that there's a few people who are allowed to do this and it needs high specific labor force, etc. It's not required. So it is that this material actually, its omnipresence on its ease of manufacturing has the potential actually here to bring a society, to tell a society, okay, put your hands, your work, your money there where your mouth is. So,
yeah. Well, this was nice said. I fully agree. Yes. Yeah. Well, I think it's I'm very mind blown. My head is still thinking about applications. Yes. I just want to give the audience the chance if there's now a question. I'm not sure if they're too shy about the topic because it's not the main background maybe. So we have one, please. Go ahead.
Hello, I'm Olaya from Cementos Molins, and I just wanted to know if there are any specific type of cement more suitable for this kind of applications, or if Mr. Joseph has tested one specific with some special additives or characteristics of this cement to perform better.
That's a very good question. No, the answer is there is no requirement, specific cement which is required for this application. It can even be used with so-called green cements, cements where you have a replacement of classical cement by some other type of fired clay type materials. So you can use it with any oxide-based cement binder, even with geopolymers, which allows you to control the porosity. That's the key factor. So the key of the technology, there are three elements of this technology which are important. One is the electron conductive material, the electron conductive network. This volumetric wire requires that the binder phase, so the cement or whatever other things you can use. Can imagine you could use clay for that, for instance. One is hydrophobic. So hydrophobic is the carbon black. Hydrophilic is the binder, because you need this opposition in order to create this volumetric wire. So that's one parameter of it. The second one is you need the pore space for the electrolyte, and this pore space needs to be continuous so that it reaches this carbon black and the carbon black and makes use of the surface. So from that point of view, if you think that through, there's any type of binder phase which allows you to control those two things, hydrophilicity on the one side, and the connected pore space, can be used for that type of application.
Okay, thank you.
You're welcome.
Thank you very much for the question. So I think there's time for one more question. Okay, maybe then I take the chance again. I was wondering what will be the next steps, like the next projects ahead. You mentioned there will be now the more bigger scales and engineering part, but can you say any specific topic you are focusing on, or is it very open?
No. So I have more questions than answers, right? You know, that's the work of a scientist. So we, on the one side, we right now we are developing these prototypes for column, for instance, right? But what we want to launch over so one area where we would like to go is to make this a technology for the global south, because we need to be all aware that Germany, Austria, Europe, the United States will be able to make the energy transition. But what about technology for the global south in order to achieve this here? So we want to launch actually a competition for to call upon people and their creativity to produce structures, sort of these batteries, so the equivalent of a 12-volt battery. And the reason for that here is not only in voltage, but also in current. The reason for that is that this becomes sort of the elementary building block for the solutions. I would say this intermittent storage here is not far off. So this we would like to bring out to the larger public. In our labs, what we are focusing on are very specific applications. So I'm most interested, and I'm only one researcher of quite a few, is on the electromagnetic induction phenomenon. To bring, actually, right now we are having basically DC charges. In order to go to the self-charging, you need to have AC at high frequency, so higher than normal frequency. And then you need to have some layer in between in order to make this happen. So that's sort of on this application, I'm working both on the theoretical one, because the highly heterogeneous material, as well as in the lab. But having said this, this is too big than just to leave it to MIT, right? So this is the reason why I accepted to talk all to you, to show you what we know. And some people always think that, when you get someone, oh, he only says that what he wants us to know. No, it's really that what I know right now. So jump in, get your hand into it. We need this energy transition.
Yes, I really appreciate a lot your way to work on this and to share the information, and also regarding where to focus on the projects, like regarding, as I said, Europe has very different chances maybe than in different countries, and this is very thoughtful to not only think about their own profits, but also about projects which can really bring everything forward. I mean, this is why we meet here internationally. So I'm very glad you joined. And yeah, I hope I know in the audience, I know some names and they are working on maybe similar fields. So maybe this could be a little first step. And I'm very happy to share also the talk later and the information. Maybe also in our institute, I can talk later to some colleagues. We are mainly focused on thermal storage, but nevertheless, I think it's very, very important to bring forward. There's one thing I can already say now. I mean, we talked before a little bit about the energy TCP tasks. I know that they are not so well known everywhere. It's just not easy to reach out to everyone. But you mentioned the example with the de-icing. And I know that there is one task, 38, which is only focused on de-icing, which is, I'm very sure until now they do not use your solution, cannot be, but I think it would be nice if you connect. So if you want, I can later just write an email to the task leader and to you, and maybe there's some nice information to share. But at the end, it's about what is the best technology to use and the most sustainable and the easiest one. So I think this could be nice first step.
Okay.
Yes, and okay. Yeah, thank you again. I could ask some more questions, but I think we have to stop now. I still have to make the advertisement for the next seminar. But very happy that you joined. Thanks a lot for making it understandable for the audience. I mean, at least for me, and this is not my specific field, so many thanks.
Thank you very much, and Merry Christmas to you all. Please stay
Yes.
safe and healthy and make the energy transition happen.